Good morning. So again, thank you for this kind invitation. So I'm going to talk about uh, a topic that you may have heard about, AI. And what is actually very interesting is these days it's actually gone beyond what techies like all of us talk about to now even prime ministers, presidents of various countries, right, are talking about AI because of the enormous impact, right, it is having on the entire world. Uh, so I come from Google DeepMind, where our mission is to build AI responsibly to benefit humanity. And we do believe, especially my team, which is based in this part, Asia Pacific region, India and Asia Pacific region, more than half of humanity lives in this region. So we take it as our responsibility to make sure we take the humanity part very seriously. Uh, and before I talk about some of the mainstream directions, one area which I did want to highlight, because it has not received as much attention in India, and again, for good reasons, we are very driven by kind of business needs, right? Immediate business needs. We are into quick commerce, right? I mean, quick gratification, which is why you have people like Goda, right, helping us get that whatever, quick commerce delivery within 15 minutes and so on. But I think beyond just quick stuff, right, we have to worry about profound stuff too, which takes time. That doesn't happen in 15 minutes, right? We have to worry about things that don't happen in 15 minutes, that take years of work, but which make a profound difference to the world. And that is science. We must not ignore science. And one of the things which is happening is that we are seeing potential for AI to actually revolutionize scientific discovery. And one kind of a interesting signal came from last year's Nobel Prize in chemistry, which went not to chemists, not to chemistry researchers, it went to computer science researchers. For the first time in Nobel Prize history, there were actually two different Nobel Prizes which went to computer scientists. And protein folding, in particular, very close to my heart. In fact, that machine, Blue Gene, that we built, one of the motivating applications for that was protein folding. In those days, it used to take about an entire PhD to uncover the structure of a single protein. And why is proteins important? You all know from your biology, right, that proteins are the basic building blocks of life. Everything that we do, the fact that I'm able to stand here, talk, you're able to listen to me, and do other things. You're able to breathe, live, and so on. It's all possible because of proteins. And proteins are made of these chains of amino acids, and they fold into a particular distinct shape, gives the protein its distinctive properties. And what is that shape that that chain of amino acids will take? It used to take about 3 to 5 years of research, an entire PhD equivalent, to uncover the structure of a single protein. And which is why, I mean, my colleagues, when we were working on this machine Blue Gene, they were trying to simulate it using ab initio molecular dynamics, that let's run lots of computations with laws of physics and hopefully uncover the structure of a protein. There used to be this contest. Every 2 years, there would be a contest called CASP, when for newly discovered protein structures, they would be given as exam problems to these models that were competing to predict the protein structure. So in the CASP, there was a CASP 13 competition in 2018, where instead of this whatever high-performance computing-based solution, there was a AI-based solution called AlphaFold, which won the top prize. And the next CASP competition, which happened in 2020, CASP 14, the predictions of this AlphaFold, which are shown in blue, they were so close to the ground truth, the actual protein structure, that the community considered the protein folding problem effectively as solved. They stopped with these CASP competitions. They said this problem is effectively solved. I mean, the predictions weren't always very accurate, but there was also a prediction of what's your confidence of the model in your prediction. So if it wasn't confident, it will say, I'm not very confident. But this was considered a breakthrough. And in fact, then this team at DeepMind, they made predictions of structures of all 200 million proteins known to humankind, and they made them freely available. So think about it, 1 billion PhD years equivalent of research that was done in a few months. Because now, the process that used to take prediction of protein folding, or whatever, prediction of protein structure, which used to take several years, it could now be done in a few seconds with the help of AI. So they made these freely available, and today there are over 2 million scientists using those predicted protein structures for their research, ranging from drug discovery to even things like designing an enzyme to make plastics degradable. So the point here is that a single, what our founder Demis Hassabis for Google DeepMind, one of the Nobel Prize winners, calls it a root node problem. That when you solve these root node problems, they can unlock so many solutions to all kinds of problems, right? So I think it is very important for us in India to pay more attention to those root node problems. Solve those root node problems, and you will have much bigger impact. Yeah, it will take more than 15 minutes, but it will take years, but you will have huge impact. So another pesky problem is weather prediction. And in fact, I remember, most of you are very young. When we were growing up, there used to be this amazing cartoonist, R.K. Lakshman, whose cartoons used to delight us every day. And he would show, I remember his famous cartoon, there's this bright sun, and there's a guy holding an umbrella. And who's this? Oh, that's the weatherman. Because the weather predictions used to be so inaccurate. And then a lot of high-performance computing got applied to make now these predictions are far more accurate. And again, we have seen AI-based models just take all of that data. And instead of coming up with those physics-based models, we've started to have these AI models make these predictions. And today, we have this model called GenCast from, again, my colleagues at Google DeepMind, which is outperforming the state-of-the-art European Center of Medium Range Forecasting, their model, ECMF models, like in 97% of the cases, it outperformed in terms of accuracy, and this runs far faster. So I don't know how many of you realize Google is now also one of the world's largest weather forecasting agencies. Now when you do Google search, because a very common search query is weather. Certainly, whenever I'm traveling to any city, especially outside the country, one of the first things I do is, okay, do a weather forecast to see what kind of clothing, right, I should pack. Now, many of these forecasts are actually served by these AI models. So on these, and this is not the only case, be it material science, be it clean energy. So in clean energy, fusion holds that potential for abundant clean energy. Already, fusion happening on sun is the source of all energy on Earth anyways. But now in a controlled lab setting, can you produce more energy? Today, fusion takes a lot of energy to get it going in that lab setting. So you end up putting more energy to get that fusion reaction than what you get out of it in that controlled lab setting. So researchers believe that we will reach that break-even point within the next few years, when we will get more energy out of that fusion reaction that goes into. And a lot of that is all the plasma controls in those tokamak reactors. They are being controlled using reinforcement learning. So in many, many very, very important areas, AI is being used to now accelerate scientific discovery. And certainly, my team is now beginning to do some work in this area, and we are also trying to collaborate with some of the key researchers in India at places like ICTS, TFR, NCBS and so on. We are, in fact, organizing a workshop soon on this. But now back to more mainstream business-oriented topics. I'll start with a very quick kind of revision or something. And in fact, AJ gave a wonderful, you might say, a tutorial, which makes at least some of my slides quite redundant, and I don't need to even cover them, or I'll cover them very quickly. Then I'll talk about the amazing advances you have seen in areas like creativity, which weren't quite expected. Because if you go back 10, 15 years, even the experts were predicting that AI would be used to automate all of these mundane tasks that we do as humans, and creativity will remain this uniquely human endeavor. And we see, again, AI helping create some beautiful art. Then I'll talk about this topic close to my heart, inclusive AI. How do we develop AI in a manner that works for everyone, especially the billion-plus people in India and in these regions of the world? And some of it would have relevance for, I think it is important for us as, in fact, a lot of the speakers have been pointing out, and in fact, which is a driving theme for this conference, for this event, how do we become more of producers of technology rather than merely consumers? And finally, some open challenges and takeaways. So, okay, so I don't need to explain this to this audience, that deep learning, right, has made this comeback. Old technology, artificial neural networks, roughly loosely inspired by how the human brain works. And while, as AJ mentioned, with these deep neural networks, there is this universal approximation theorem that states that even with a two-layer deep network, any computable function can be approximated, including things like, given an image, can you classify that image? Is this an image of a cat or not, or a dog? And what we saw in the last 15 years is starting with the breakthrough, right, where deep learning made a comeback on this image classification problem. Very soon after that breakthrough, on a broad bunch of different problems, like speech recognition. Given an audio signal, can you recognize the words? Or machine translation. Given this text, can you translate it into a different language? There were all these decades of work in machine learning-based algorithms for all of these problems. And what happened in the first wave of deep learning was that deep learning-based methods started doing better than all of those previous machine learning-based methods. And it was very surprising how this one approach, deep learning, worked so well on such a broad range of applications. So you may say, OK, life is good. What else do you need? There were two things very unsatisfying about this. One was, often you needed lots of annotated data to build these models. Often these were built using millions of annotated images, millions, and often like hundreds of thousands of hours of audio, millions of parallel sentence pairs before you could make these deep learning models work. That was one problem. The other, for every problem, you had to train a new network pretty much from scratch, which is not how we humans learn. Given a new problem, we don't start from scratch. We build upon our years of learning, and we build upon our experience with similar problems in solving a new problem. And that is what got addressed through this new emerging paradigm, which is foundation models. And it was enabled by, again, another major research breakthrough, the transformer model, which is presented famously in this paper, Attention is All You Need, at NeurIPS 2017. And one of the first foundation models which was built before the term foundation models was even coined was this model called BERT, where this T stands for transformer architecture. And they use the transformer architecture on this problem of what I call fill in the blanks, where they took this piece of text, all this text from Wikipedia, digital books, and so on, they masked out 15% of the words, and they started training a model to predict those missing words. So this masking out was this clever trick to use self-supervised learning, right? Instead of having to label all this data, if you hide that data and train a model to predict that data, you already know what those hidden words are. So you don't need to now do an annotation of the data, right? The annotation is there, right, inherently in the data. So that's the idea of self-supervision. And to predict this word born, they use this transformer architecture, which would use that all of the text in a certain context window, do all those matrix multiplication, right, that AJ was showing you, and magically, almost magically, using this transformer architecture, it like figures out the right weights for these different words, like the words Obama, 1961, Hawaii. These would influence the choice of the word born. And as you do those matrix multiplication operations, kind of the training process, you discover the right weights, and you're able to predict the word born here. So now this may remind you, right? At least it reminded me of this fill in the blanks exercise my teacher, English teacher, used to give us in school. And through that exercise, the teacher was testing our ability to understand the language and also reason about things from the context. So just like that fill in the blanks exercise, when it was given to this model, BERT, once it became good at that, it wasn't just predicting those missing words very well. It was solving a whole bunch of other natural language processing problems quite well, including like sentiment analysis or question answering, summarizing piece of text. It was giving you a very good starting point. So fast forward to a few years later, there was this model called PaLM that my colleagues at Google Research built. It had 540 billion parameters. AJ was showing you, right, all those networks with neural networks with what looked like a few hundred parameters. This had 540 billion parameters. And they did this interesting exercise. They took this benchmark called Big Bench, which had 58 different benchmarking tasks. They compared the performance of this one model, PaLM, with the best known model for each of those 58 tasks. Best model. And this plot shows the relative performance, relative quality. So these bars in whatever orangish color show that the specialized model did better. But all of these bars show that that one model, PaLM, did better than the specialized model, the best known specialized model for that task. So it is phenomenon like this which led Stanford researchers to coin the term foundation models. That today, when you're solving a problem, you don't kind of solve it from scratch. You don't have to train a new model. You can start with these foundation models that are providing you a very, very powerful starting point for these models. And the other interesting thing that researchers found was that it was also able to solve not just a whole bunch of NLP problems, but even some mathematical puzzles, which required some math-based reasoning. But like it could solve a problem like this. John takes care of 10 dogs. Each dog takes half an hour a day to walk. How many hours a week does he spend taking care of dogs? They saw that it could solve this problem, but only if it was also given similar problems that required similar mathematical reasoning, and not just similar mathematical reasoning, it was also shown step by step how to solve the problem. Again, reminds me of the instructions from our math teacher in school. Don't just solve the problem. Show me step by step how you have solved the problem. So now, if you show this model, PaLM, step by step, how to solve this problem, and again, this problem you see here, this is not syntactically very similar to this problem. I mean, here we are talking about John and dogs. This is talking about Sean and toys. So the syntax is very different, but the concepts are the same. So this model is able to generalize from like those concepts from a very different problem, but as long as it is shown step by step how to solve this problem. Because if it is only shown that problem and answer, then it gets this problem wrong. But if it is shown step by step, then it gets it right. So that is what these researchers call chain of thought prompting. And chain of thought-based reasoning is now letting these today's models even solve like international math Olympiad kind of tough problems. In fact, a model based on Gemini, the reasoning version, and a model from OpenAI, they reached the gold medal level performance in the latest international math Olympiad. The other thing was, it wasn't just working for text, it was also working for other modalities, for images. A lot of medical early work on AI-based medical imaging was annotate lots of these medical images where, let's say, you're doing breast cancer detection, annotate those mammograms or thermography-based data with, is this a case of cancer or not? And then use that supervised learning. But now, what the researchers found was that if you take even unlabeled medical images, built good models that had good representations, and then fine-tuned those models with some labeled data, started doing better. Same story with speech recognition. At Google, we used to have models for each language, trained on like over 100,000 hours of annotated speech data. Instead of that, you now take millions of hours of even unlabeled speech data, train a model to come up with good representation, and now you fine-tune it with even 1,000 hours of labeled speech data for a language. It starts understanding that language better than a model with much larger amount of purely labeled data training. So which brought us to this, in fact, that Palm model, Google never launched anything because we were concerned about all the biases and potential harmful users and so on. And meanwhile, there was a company called OpenAI, which launched something called ChatGPT. And they showed the world that despite all of those kind of issues, open issues with those models, millions of people found ways of getting some good value out of those models. So that prompted, competition is a good thing. It prompted then Google to build this model called Gemini, which also has all of these amazing capabilities. And in fact, of course, we wanted to go beyond anything from the state of the art. So one of the capabilities where Gemini excelled, so this is the Gemini 1.5 model that was launched about 18 months ago in February of last year. Two things that it kind of, where it was particularly strong. One was multimodality. While these are known as LLMs, it was no longer just a language model. It was operating on a lot of modalities, speech, images, videos. And it brought this long context capability, 1 million tokens of context that it could handle. And what that meant was like several equivalent to dozens of textbooks, right, that you could give as part of your input prompt, or an hour of video that could be given as input prompt. So let's take a look at one example which shows what it could do with like a 45-minute video.
This is a demo of long context understanding, an experimental feature in our newest model, Gemini 1.5 Pro. We'll walk through a screen recording of example prompts using a 44-minute Buster Keaton film, which comes out to over 600,000 tokens. In Google AI Studio, we uploaded the video and asked, find the moment when a piece of paper is removed from the person's pocket and tell me some key information on it with the timecode. This screen capture is sped up, and this timer shows exactly how long it took to process each prompt. And keep in mind that processing times will vary. The model gave us this response, explaining that the piece of paper is a pawn ticket from Goldman & Company pawnbrokers with the date and cost, and it gave us this timecode 1201. When we pulled up that timecode, we found it was correct. the model had found the exact moment the piece of paper is removed from the person's pocket, and it extracted text accurately. Next, we gave it this drawing of a scene we were thinking of and asked, what is the time code when this happens? This is an example of a multimodal prompt, where we combine text and image in our input. The model returned this time code, 1534. We pulled that up and found that it was the correct scene. Like all generative models, responses vary and won't always be perfect. But notice how we didn't have to explain what was happening in the drawing. Simple drawings like this are a good way to test if the model can find something based on just a few abstract details, like it did here. These are just a couple examples of what's possible with a context window of up to 1 million multimodal tokens in Gemini 1.5 Pro.
So I don't know about you. I mean, I found it magical that now you could kind of analyze these AI models, could analyze contents of videos, right, and give you answers. So today, you can take many of these videos and you can kind of pose questions to these models, and answers won't always be accurate. Many times they are wrong, but it's still amazing how so many times you're able to get these models to provide those answers. And so there are many, many applications of this long context. One of them is enterprise scenario. The enterprise kind of data that could not be used for training the model, right? Because this is proprietary to the enterprise, that could be given as context. Or Goda talked about the need to personalize the model, right, to a user. You could now give it the user's history as part of the context, right, along with the query. You could append some information about the user's context so that that user's context is still private. It has not been used to build the model, but it is now taken into account by the model while doing those predictions. Another very cool use of this in-context learning, which I really loved, was this example, where there was this language, there is this language called Kalamang, which is spoken by barely 130 people in the world. Very few resources of this language. So if you kind of make these models ask a question in Kalamang, they won't understand. But there's also a book, of a 573-page book written on the grammar of Kalamang. So if, in addition to your query, you feed it also that book, plus the dictionary, English to Kalamang and Kalamang to English dictionary, along with the prompt, now this model starts to perform at the level of a human learner. So this is really, really powerful in-context learning, which is happening because of this long context. Then we launched this Gemini 2.0, where we started to now showcase some agentic capabilities.
Gemini 2.0 enables new kinds of multimodal AI agents. Agents that can see and hear the world around you. Think, plan, remember, and take action. Gemini 2.0 is what enables Project Astra, our research prototype of a universal AI assistant. Using capabilities like multimodal memory and real-time information, it lets you understand your world, live.
What can you tell me about this sculpture?
The sculpture you're seeing is called My World and Your World by Eva Rothschild, located in Lewis Cubitt Park in London.
What kind of themes does her work explore?
She creates abstract sculptures that invite viewers to interact with and interpret their surroundings in new ways.
Project Astra is multilingual, using native audio to seamlessly switch languages as you speak.
Est-ce que tu peux me dire quelque chose d'intéressant à propos de ces lanternes?
Bien sûr, je peux vous parler des lanternes. Les lanternes que vous voyez font partie de la porte d'entrée de Chinatown à Londres. நிச்சயமாக இது லண்டனில் உள்ள Chinatown நுழைவாயில்.
We're taking this to the next step with Project Mariner, with agents that can complete tasks on your behalf. You can ask it to do things like this that require multiple steps, doing research to look up the artist, then finding the painting, and then shopping for the right supplies. The agent uses the web to take action and find what you're looking for. It plans and reasons at each step, always staying in your control and completing your task. Gemini 2.0 enables agents that can be applied across domains. We're exploring agents that can explore virtual worlds, assisting you in video games.
Where do you recommend I attack from on this base?
Given the base layout, I recommend attacking from the bottom or south side. This direction allows you to target the town hall directly with your giants, while the wizards can handle the surrounding defenses.
Gemini 2.0 can reason about the physical world, understanding 3D spatial environments and objects. These capabilities are being applied to robotics, with agents that can assist you in your everyday physical environment. Learn more about how Gemini 2.
Let me also skip. I mean, another thing which is becoming very popular is this whole term vibe coding, where instead of using the programming language, you're now kind of giving prompts in natural language English, and these models start kind of churning out code. And you can here also give code and, I mean, English and in text and image-based instructions. But the other interesting thing we have seen with all of these Gen AI-based models is this amazing advances in creativity. Today, we are writing drafts of emails when creating presentations, often because I'm very challenged, visually challenged. So instead of now all those boring bullets, I often now try to create some appealing images using all these text-to-image models and so on. And the quality of these models is quite astounding these days. I mean, so these are examples of images that have been purely automatically generated by an AI-based model, in this case, Imagen 4 from Google. And again, you can see the level of quality in these. And beyond images, videos is the other exciting part. And one thing which we introduced with VO3 was the missing piece. Earlier, all these AI-generated videos were silent videos. So now we said bye-bye to the silent videos era with this audio generation capability. So this is an example of an animated movie clip generated all automatically. And this is a more realistic, you might think of it as almost
this
like
ocean, it's a force, a wild, untamed might. And she commands your awe with every breaking light.
So the actor, the soundtrack, including those waves in the background, the voice, the dialogue that was delivered in a fairly natural style, the lip sync, all of this was AI generated. So you can see the days not far, right, when Hollywood, Bollywood would be using these technologies in a big way. Another very important aspect of creativity is music. And there was this fun partnership that the Google team did with Shankar Mahadevan at helping him create even more music.
We kick in the dolak and all when the roo comes in. Working with Sandbox is great. We inputted our requirement and it gave us a bed. We used that bed and we came up with the song. It became a beautiful combination of very traditional Sufi melody on a very modern track. I think creating the melody is the most favorite part. When that feeling comes, you really feel proud of yourself.
So with these models, what we are trying to do is not replace the human artists, but both, as one of my colleagues says, raise the floor as well as the ceiling. Ceiling is where we work with artists like Shankar Mahadevan, and we are helping them explore different options and help them create even better music. Or it could be raising the floor, right, where it could work with somebody like me and help me create some music, which I otherwise would not be able to. So, which brings me to I would say, the more important topic of inclusive AI. How do we develop all of these technologies in a manner that really works for everyone? And what we saw was that all of these amazing capabilities that we saw, kind of with models like Gemini, they worked very well for a language like English, not so well for languages like Hindi, even worse for then languages like Gujarati, Assamese, and so on. So our team created this benchmark, Indic GenBench, which was presented at ACL conference last year, where we created this benchmark with over 100,000 tasks spanning things like cross-lingual question answering, translation, and so on. And we saw that every model, including ours, here higher number is good. These blue stars show the performance in English. And we saw that every model was doing much better in English compared to this bundle of Indian languages. So our team has been working on this model for Indic languages. Our first attempt was a model called Mural, which we had built in 2020, I believe, if I remember correctly. And it that time provided the largest coverage of Indian languages, 16 Indian languages and English. And when I challenged Partha Talukdar, who built that model, to make it work for all 22 scheduled languages of India, I was very happy to see him come back and show me this data from Language Survey of India, which showed that there are 60 Indian languages which have over 1 million speakers each. There are close to 125 languages that have over 1 lakh speakers. So he said, let's build a model that understands all of those 125 plus languages. Easier said than done, because then he also told me that 72 out of those languages were zero corpus languages. There was zero known digital data on those languages. The other challenge that we all know is the same language is spoken in so many different ways. I'm a native Hindi speaker. The way I speak Hindi is very different from how a speaker from another state. So I'm from Haryana. The way my Hindi, but brought up in Delhi, so my Haryanvi and Delhi Hindi would be different from how a speaker in Bihar would say versus UP and so on. So, and there is a saying in Hindi, "Kos kos pe badle pani, char kos par vani," which means every few kilometers the taste of water changes in India. Every 10 kilometers the nature of voice changes. So that saying inspired this project called Vani, which we launched together with Indian Institute of Science, where we started collecting speech data from different corners of India. We are in the middle of phase 2, and we have made data from 143 districts so far freely available. It's freely available for anybody to use as you build your AI models. It covers over 27,000 hours of audio, and it already covers over 100 Indian languages. And out of those, at least 22 of these used to be those zero corpus languages. So this is the first known digital data for at least 22 of those languages. And this is also the first speech data for 35 of those languages. And it's heartening to see, I've seen like startups like Shunya Labs, they recently posted something on LinkedIn where they've built some of these speech models making use of this data. And we'd like to, again, see many more companies utilize data like this. So for us, the natural problem was, yes, we built that model Morni that understands Indian languages very well. How do we marry it with a model like Gemini that otherwise is extremely powerful, but only works well for most other languages like English and other more common languages? So our team came up with this methodology called CALM, which was presented at iClear conference last year, which is using the cross-attention mechanism. This is a way to take two already trained models, keep them unchanged, create a new fused model that has the best of both worlds using the cross-attention mechanism. For us, the motivation was to make Gemini understand many more of these Indian languages, but you can use the same idea to also make a generalist foundation model, compose it with a specialist model like for healthcare, for coding, and so on. And we have, of course, been using it to make Gemini understand Indian languages very well. And our benchmarking shows that currently, the top performing model when it comes to this collection of Indian languages, here we are using, again, that same Indic GenBench. So the top two models are, Gemini 2.5 Pro. Flash is the efficient versions of Gemini 2.4 model. In many cases, even the Flash version is doing better than GPT-5. But these are currently the top 2 models. And we would like, again, more models built in India. So certainly, I can claim that, yes, significant parts of the Gemini 2.5, at least when it comes to Indian languages, are built in India, built by our team. Would love to see more and more models that start to do well, because the gap is still quite significant between how these models work on Indian languages versus languages like English. But one power of foundation model that you see at work is that when you build such models, tasks like machine translation, we certainly saw that with the precursor to Gemini model, something called Palm 2, when our team built this version of Palm 2 called Palm 2 NTL, which understood over 1,000 languages of the world, we saw that for several languages, this model was now doing a better job at machine translation than our translate models. And that powered the expansion of Google Translate product. In one shot, the team added 110 new languages, covering basically spoken by cumulatively over 600 million people, all in one shot. One model, and it is now doing a better job of translation for all of these languages. Our team, so I showed you kind of that Astra tool in that demo. So we wanted to apply Astra in the setting of learning, which we believe is very, very important, and to make it work for Indian languages. So that's one of the things that our team is working on.
And let's take a look at how Gemini can help.
Kind of where we are.
नमस्ते।
क्या आप क्वेश्चन 3 सॉल्व करने में मेरी हेल्प कर सकते हैं?
हाँ, मैं समझती हूँ कि आप चाहते हैं कि मैं इस इक्वेशन 3x² + 5x - 2 = 0 में x का हल निकालूं। क्या आपने इसे ट्राई किया है और क्या आप मुझे इसके स्टेप्स दिखा सकते हैं?
हाँ, मैंने क्वाड्रेटिक फार्मूला यूज किया है। क्या ये ठीक है?
हाँ, ये सही तरीका है, पर आपने डिस्क्रिमिनेंट में एक छोटी सी गलती की है। आपको कोएफिशिएंट c के आगे एक माइनस साइन छोड़ दिया है। सही कोएफिशिएंट्स हैं a = 3, b = 5 और c = -2। इसलिए सही एक्सप्रेशन 25 + 24 होगा, न कि 25 - 24। एक बार जब आप इस मिस्टेक को करेक्ट कर लेते हैं, तो सही उत्तर 1/3 और -2 होगा।
Thank you.
So I'm not going to claim that this model will work this well on every problem, but I can assure you, no cheating involved. This was purely an AI model looking at this handwritten kind of solution to a math problem, conversing in kind of a combination of Hindi and English, and helping the learner figure out where they went wrong. So this gives me hope, right? That the dream we've had of a personalized tutor available to every child in our country now seems within reach. The other thing our team has been pointing out is that it's not just a matter of understanding different languages. These models need to understand different cultures. That when you're responding to a user in Assam, you shouldn't just come up with a response in English and simply translate that into Assamese. You should come up with the response rooted in the cultural context. You should understand the culture of Assam before coming up with the response. Areas like agriculture, so our team has built the first such model at national scale based on satellite imagery, which is able to identify things like field boundaries, identify sources of water, classify the crops that are being grown. So that model is freely available under a trusted tester program. And our hope is to unlock use cases like loans to farmer, crop insurance. Today, let's say, if the farmer wants to buy insurance for cotton crop, the insurer has no way of knowing, is the farmer actually going cotton or not? I mean, because their farm could be hundreds of kilometers away from the insurance company's offices. Now they can quickly check what crop the farmer is growing. And again, it required overcoming a whole bunch of challenges like spatial, because farms in India tend to be very small, spectral, because for much of the monsoon season, much of India is covered with clouds, temporal, because you want to identify these crops as early as possible, well before harvesting, and this should appeal to AJ. I mean, he was talking about efficiency of all of these models. This is an area where I'm very proud to say our team based in Bangalore is amongst the global leaders anywhere in the world. Certainly within Google DeepMind, we are recognized as amongst the best teams at Google, working on making these models very efficient. One of our breakthroughs was enabling elasticity of these compute models. In fact, Goda made a reference to this Matryoshka embeddings. The name is inspired by the Matryoshka Russian dolls, which are nested one inside the other. But this is not a Russian technology. This is built in India. Where while coming up with the embeddings, it started with that question, can you build this, let's say 128-bit embedding in a manner that the most significant bits encode the most useful, carry the most useful signal, so that you could chop off that embedding at any point. So today, we are very proud to see not only do all of the major Google embedding models use this, pretty much every major model in the world is using Matryoshka models. In fact, there was an interesting tweet that came from OpenAI, I think it was almost 2 years ago, where they claimed, oh, they have this amazing innovation. And then there were sarcastic videos pointing out, oh, you're talking about Matryoshka model embeddings. And then they admitted, oh, yes, sorry about the oversight. It is indeed based on Matryoshka embeddings. We extended that idea to then transformers, so that when you build this, let's say, train this transformer block, instead of only training it for one size, let's say XL size, extra large size, I'll train it simultaneously for 4 sizes, large, medium, small. And when I built these models using multiple layers, I can mix and match those different sized models from different layers. And what we found to our surprise was, even though you had only trained kind of these models for 4 sizes, through this mix and match, we found that these automatically derived models were performing very well for a very broad range of applications. So today, many of our Gemini models are now built using this Matryoshka model. So when Google built, let's say, the Gemini 16 billion parameter model, we made, using Matryoshka models, we made 8 billion, 4 billion, 2 billion, 1 billion size models available to all of our product colleagues. And we showed that these independently derived models were doing as well, or sometimes even better, than a Gemini model that was built specifically for that size, because of some code distillation which was happening, because the techniques that we were using. So there were some learning transferring over from larger models to the smaller models. And the same idea got used in this model called Gemma 3N, which is now on these mobile devices like this one. And now, because on a mobile phone, you only have space for one model, but now using this, because it's trained using Matryoshka methodology, that one model has many, many smaller nested models inside. So now an app can choose to say, let me use that intermediate size model, or let me use that smallest model, because now that will preserve battery life. So very proud. So that innovation came out of our team. Then there were a whole series of other innovations on efficiency that came out of our team. I'm out of time, so I won't take you through all of them. I'll just give you a very quick idea, conceptual idea of some of them. So today, these models do this decoding, the generation of response in an autoregressive manner, which is one token at a time. And because it is one token at a time, it's very slow, sequential process. So our team had this idea, what if you used different models for prefill versus decode? What if you use a smaller model in tandem with a larger model, which is paying attention to the larger model's KV cache representation and generate this? It led to significant improvements in efficiency. This attention layer, when I was showing you that long context example, that video was speeded up. that one query was taking almost a minute to respond. So that long context is extremely expensive because the computation scales as n square. If n is the number of tokens, the attention computation is order n square. Here, with Treeformer, we are trying to train a network and a decision tree jointly, and we are trying to bring the computation closer to n log n. If through the tree, we can direct it to the appropriate cluster, and if that does most of the magic, then the computation could be brought closer to n log n. And this higher idea where when you're doing reduction computation over, let's say you're doing max computation over 1 billion elements, can you inexpensively estimate which are the top, let's say top 1,000 elements, and then do the max computation only over those top 1,000 elements? So that was the idea behind higher. But the basic upshot of all of this is that with all of these techniques, we've been able to make our Gemini models, like these have gone into Gemini Flash, the most powerful per watt, per dollar, per rupee, and so on in the industry. In fact, higher than DeepSeek, which people thought kind of brought about a new paradigm. The point is that all of this innovation was done right here in India. So we are capable. So it drives me mad, right, when people say, foundation models are inherently expensive to train. Forget about, in India, we can't do it. No, we can. It requires guts. It requires ambition. There's no kind of magic that this is something that, whatever, only a few people in the Bay Area kind of know how to do. All of these things can be done. In fact, I would also say that there are so many open challenges. I mean, if you look at the efficiency, there's still so much room to cover. You look at today's models, right? These are already approaching, and in many cases, on certain aspects, surpassing human intelligence. But these models take gigawatts of power. And how much power does human brain takes? It is estimated about 20 watts. Look at the headroom available. I'm not saying we know how to get it to 20 watts, but that's the headroom which is available. In nature has shown it is possible to do those computations at roughly 20 watts. So there's still a lot of innovation to be done on making things more efficient. Also, I mean, you all know about the hallucination problems and so on. Reasoning. I would say today the way reasoning is being done, even by our models, I mean, it's almost like rote reasoning. It's almost like you have just shown these models every question and answer ever written. And they've kind of somehow mugged up all of those question answers, and now they're, through some reinforcement learning and so on, they're able to now do some generalization. But in my view, there is still a breakthrough needed, where the equivalent of Newton's equation or Einstein's E is equal to mc square. I want to compute how much energy is produced, right, when whatever these atoms collide and so on. These models are still unable to kind of understand concepts, relationship between concepts, and so on. So in my view, there are still a lot of breakthroughs to be had. And so I think it is very, very important for us in India to start building these foundation models. It's good to see companies like Sarvam, Socket, many of these companies have started to build foundation models out of India. In my view, our companies also, startups also need to become more ambitious. We shouldn't be aiming just for, because sometimes it still bothers me when I hear the ambition, I want to build the best model for these Indian languages. We should aspire to be, maybe that can be the starting point. We can aspire to be not just the best in India, we should aspire to be the best globally. Today, I mean, our neighbor, right, to the north, they have shown, they have all of these companies which are building their own foundation models, which are, again, very, very competitive. So, and it's not just one organization. It's not just DeepSeek. There are models from Alibaba. There are models from Baidu. So I would love to see in the future, right, models coming from the InMobis of India, the Swiggis of India, the Flipkarts of India, which are competitive globally, which are giving Gemini a run for its money. I would love to see that. And it's all possible, because a lot of these actually improvements, right, when it comes to making it understand many more languages, making it more efficient, and so on, they've actually come from, in many cases, people who are based right here in India. So there's a lot that can be done. So I would challenge the audience to, again, don't just take it for granted that, oh, we have to do only tinkering. We can only do fine-tuning of models. The real work has to be done by those amazing Zoda masters in the US, in Europe, and so on. It can all be done in India if only we have the courage, if only we have the ambition to do it. And let's build that ambition right here. So with that, let me stop. These are obvious points that AI today is impacting every aspect of the world, and it's an amazing opportunity for us to, of course, build models and solutions that will bring benefits to billions of new people because of their applicability. Very, very exciting times. Let's really show India, right, as not just a consumer of all of these models, but also a producer of all of these models and solutions. With that, let me stop, and thank you.